Hello. My name's Luke Bond. I'm going to talk about building a Docker platform as a service. In particular, I'm going to focus on multi-host Docker networking and service discovery. First of all, I just wanted to say it's great to be here. The lineup today is amazing, so to be part of this feels very special. Okay. So what I'm going to start with is I'm going to run through a few sort of problems that you would need to solve if you wanted to build a Docker platform as a service. And in particular, I'm going to go into service discovery. And I'm going to use, as an example, a platform as a service type thing that I built called creatively PaaS as a reference point. And then along the way, you're going to discuss some things about the Docker ecosystem and mostly about Docker multi-host networking. I think what I hope you'll get out of it is if you're relatively new to Docker and you've had to play with it, particularly like single host stuff, and then you want to sort of progress beyond that, you got something to run in production perhaps, or you want to do multi-host Docker networking basically, and the challenges that come up when you're trying to do that. Hopefully you'll learn some things that will help you with that kind of thing in this talk. Okay, so who am I? I am a server developer at Yield, YLD. We're a software engineering consultancy in London, and we have an office in Lisbon as well. We do mostly Node.js and do quite a lot of Docker these days. I built a platform as a service in Node.js based on Docker and CoreOS called PaaS, and you can read about it there. I'm not really going to talk about that as such today, but I'll be referencing it as just my main sort of experience with this kind of thing. Okay, so if you to build something like a Docker platform as a service, I've sort of made a little list of things that you will have to, that everyone's going to have to solve if you're going to do this. I think firstly, and this one's paramount, I think, workflow. Success of platforms like Heroku show that having a really nice developer workflow is something that really gets you traction, makes developers really enjoy using it, and it's something you need to get right. And scheduling is basically if you have a container to run across a bunch of nodes. We've heard a little bit about this today. The decision of deciding which node to run it on is scheduling. You'll need to deal with this at some point, depending what you're building your platform on. If it's Kubernetes or Mesos or Fleet or what have you, this may be done for you, but nevertheless, it's an issue. Service discovery, basically how your services talk to each other and how the request from one service to another gets routed. That's all kind of service discovery. DNS of some kind, so that things from outside can talk to services within your platform. And zero downtime deployments. In this day and age, with people doing continuous deployments, you want to have a very frictionless, you want to reduce the friction to deployment as much as possible so that people can deploy really quickly. Any commit could be a release candidate if it passes tests, that kind of thing. So you can't afford to have a situation where you need to stop some services, have an outage while a new one comes up. So you need to do something that allows you to have zero downtime deployments. In 25 minutes, I don't have time to go into all of these things, so what I decided to do, rather than, in order to have enough meat, I suppose, is I'm going to focus on server discovery in particular. I also think it's the selection of these about which I have the most interesting things to say, I think. So, cool. So, what is service discovery? Basically, if service A needs to speak to service B, service discovery is two things. One is how does A know how to address service B? How does it find it, I suppose? And then how are those requests routed from service A to service B through whatever plumbing you have in your platform? I think it's best explained with an example. Okay, so imagine this scenario. You have more than one host running Docker containers, host A, host B. We have multiple kinds of services that are running within the cluster and multiple instances of these services. So I've just made a contrived example here of something with a web service, an API service, and a database. Web talks to API, API talks to database, that kind of thing. And imagine that each service, when it starts up, it needs to take a URL as an environment variable of the service to which it wants to speak. And we can make no assumptions about the particular host on which a given service is going to be running, and likewise the ports are going to be random. And there are multiple instances of each type of service. So in this diagram, I've got two APIs, two webs, two databases, but just to illustrate the point. Okay, so you might think perhaps you could start up, say, an instance of web and pass it an IP address and port of one of the instances of the API. And But there are problems here. One is because we do have multiple instances of each service. We want to do load balancing when we're not getting that. And also, if that service goes away, obviously, then that web service has nothing to talk to and will need to be restarted to get a new one. So service discovery at startup time is not enough. We need something more dynamic than that. Another solution that might sound plausible is DNS. After all, that's how the internet works. DNS is the oldest service discovery that we all know about. I'm talking here about traditional DNS, by the way, not things like Weave DNS. I'll talk about that in a minute. But so just like on the internet, when we have an address of something, we want to have a name to refer to it by, and we want to be able to change the address that that name points to. It sounds like what we want, but there are a couple of issues with it. Sort of mostly it goes back to what I was talking about earlier, wanting to do continuous deployment with zero downtime deployments and that kind of thing. DNS is just not quite dynamic enough to support that kind of use case, at least as it is. So one of the issues is that containers don't have a unique IP address. So in order to have random ports for our different services within a host, then we'll need to use SRV records, serve records. And in my opinion, if you're building a platform as a service, then you're placing an undue restriction on the things that are able to run on your platform by saying that they have to speak your particular service discovery language, i.e. serve records. So for me, I think that's one reason why it's out. But also there are time to live issues. If you've ever launched a website, pointed a domain name at the address and waited, refreshing the browser can take 10, 20 minutes for the DNS to propagate across the internet. Internally within the cluster, we can mitigate this somewhat with the shorter time to live values, but I think still it's not quite dynamic enough for our needs. So I'd say DNS is also out. In my opinion, there are two sort of main ways you can go about this that I think will work and give you the kind of level of dynamism, is that the word? That we want for this kind of thing. So one is a non-traditional DNS solution, something that works like DNS but is something different that deals with these kind of realities. For example, Weave DNS or Flannel and this kind of thing. And also the other option is something like a dynamically configured load balancing proxy. The latter is what I have experience with, so I'll talk mostly about that, but I'm going to give an example of both. Yeah, cool. Okay, so talk a bit about Weave and Weave DNS. You'll probably hear about Weave a bit today. If we haven't already, don't think we have yet. It's becoming quite ubiquitous in the Docker ecosystem at the moment. Weave is a software-defined network in which each container gets its own IP address on the Weave network, which opens the door to DNS. Again, means we can use DNS without having to use serve records, which is really cool. So Weave also provide a tool called Weave DNS, which is basically DNS for addresses that are on the Weave network. And what's great about that is you can have multiple addresses pointing to the same name. So back from our example earlier with the API in the web and the database, you can have a domain name API and multiple IP addresses registered against it. Get something like round robining. The documentation isn't clear on whether it's round robining or not, but it gives us what we want, basically. There are a couple of things you don't get with this in comparison to what I'm going to talk about next. One is DHCP. Weave DNS doesn't yet support DHCP, but I believe it's coming soon. So you have to specify your IP addresses manually when you start your containers, whereas Flannel does do that, which is cool. And the other is zero downtime deployments. You might argue that that's not something we should ever do, but nevertheless, if we're drawing a comparison between these two approaches, that's not something that Weave will do for you. So let's look at the dynamic proxy option. So this is just kind of like a logical view, a sort of conceptual view of the problem. I'll go into it in more detail in subsequent slides. But sticking with our example of web and API and whatnot, in this scenario, you have something like web is able to route to API by the service name. So I've got this http:/API there. And the proxy's job is to, it knows about all the containers that are running in your cluster and their IP addresses and ports. And it is able to route this request through to one of them and do things like round robining and that kind of thing. And ultimately, it'll boil down to some address like that. So this is basically the ambassador pattern, whereas the proxy is acting on behalf of the services it's proxying to. And the proxy itself is part proxy and part dynamic load balancer. And bear in mind, I'm talking mostly about HTTP here, but this is a conceptual model, could apply to other things, but I'm only going to stick to HTTP for some simplicity today. And in this case, in HTTP, you would be routing by HTTP host header, most likely. And again, I'll go into more detail in a moment. So then you have the question of where do you have your proxy and how many of them do you have? You obviously don't want the proxy to be a single point of failure, so you don't want just one, of course. Would you want to have a proxy for each destination service? So like for the API, you have one proxy in front of it, like a load balancer, for routing to all the instances of API, perhaps. Or you could do it the other way. You could have a proxy for web to proxy to all the things that web might want to speak to. Or you could do both. You want to consider how many instances of these proxies you want floating around in your cluster, depending on how heavyweight they are. But I'll show you how I did it for PaaS. It's very confusing when I say PaaS. I mean PaaS with a Z here rather than with an S. So PaaS is built on CoreOS and Fleet. So that kind of influences the way we went about it. Basically, what we do is have an instance of HA proxy on every host. And by using some Docker settings and DNS mask, we're able to kind of wire it all up, and I'll explain how that works. So on each host within the cluster, Docker is configured to start each container with --DNS equals, and then the host IP, which will be caught by a DNS mask, which is bound there on port 53 on each host. So, and the configuration for DNS mask is quite simple. Basically, for any DNS requests for something that is a service within the cluster, for example, API, web, these examples from before, then it will return the IP address of the host itself, which means that the request will end up going to HA proxy because it's bound to port 80 on every host. And every other DNS request will just be forwarded onto the internet. So what this gives you is, basically all requests for all services inside the cluster will go through HA proxy, this dynamically configured load balancing proxy that works like I showed on the previous slide. Okay, so how does HA proxy get configured to have all this dynamic information about the containers in the cluster? The answer is it comes from etcd and in PaaS. But although I'm using PaaS as an example, you can actually take these concepts and do them. However, if you're not using Fleet, you're not using etcd, you can do this in different ways. But hopefully you get the principles and you can implement something similar yourself if you're using a different setup. We're using a tool called confd, which I'll talk about on the next slide, which is basically taking this information from etcd and writing it into the config file. But for now, this slide is about how that information gets into etcd. Okay, so for those familiar with Fleet, you will understand this. If not, Fleet is kind of like an abstraction for systemd at a cluster level. Rather than talking to systemd on a host saying start, stop this, you're talking to a cluster saying start, stop this. It's pretty cool. And that coordinates everything with etcd. But basically, you declare your services as something like systemd unit files. And so what PaaS does is for each container that's going to run, let's say an instance of some API service running in a container, it uses a systemd binds to directive to create a sidekick announce container. What that means is binds to means that the lifetime of one unit is bound to that of another. So when you start API service, this sidekick container will also start, and when it stops, it will also get stopped. And you don't need to explicitly do so. It will get started and stopped as the service does. And the job of this announce sidekick is to write into etcd in a particular place the IP address and port against this service name. So how it does that is basically just use docker inspect. It grabs the port that gets randomly allocated to it, and it ends up writing a list of entries like at the top there, /PaaS/services, then a list of all the services with their IP addresses and ports. And it writes this with a time to live in etcd, and it will sleep, and then it will write it again, and it will sleep. And as long as the service stays up, it will just keep kind of refreshing that. And when the service stops, the sidekick will stop, and it will stop writing it, the TTL will expire, and it will disappear. So what you have then is a constant record in etcd of everything that is running and nothing that's not running, except within a short TTL. And so we can use this information to configure HA proxy config files to do our service discovery. So on the next slide, I'm going to talk about how this information actually gets into the HA proxy config file. So you don't need to read all of that, but just to give you an idea. So we use a tool called conf-d, which is written by one of the guys from now works at CoreOS, Kelsey Hightower. It's basically a tool that can watch for a directory in etcd or a console. It also supports console. So in PaaS's case, it'll watch the directory /PaaS/services, and it uses HTTP long polling to be notified when anything changes. So what that means is that anytime a new container is started, or a container is stopped, crashes, dies, whatever, or moves from one host to another, that means that that value is that the change is constantly being detected by conf-d, and it takes that data as JSON, and it puts it through a Go text template and renders an HA proxy config file. You can imagine it as something like, if you've done web development, something like Handlebars rendering an HTML template, but this is rendering an HA proxy config file with data from etcd. Am I back? So what I've got here is an excerpt from one that's been generated by conf-d. We have one front end and two back ends. You have one front end is basically, it's kind of like binding to a port, so you have one on port 80, obviously, and you have a back end for each service. In this case, I've just got two contrived examples, one called My Service and one called PaaS Web, which is the PaaS Web UI. And at the top, in the front end section, we have a set of rules, and one for each back end. So basically, it's saying for anything that by HTTP host header it knows is for my service, it will route it to the backend. It will use the backend called my service, and then you can see below that says balance round robin, and it has a list of nodes. And this is what the HA proxy config will end up looking like, but you can imagine it being like much bigger if you have a bunch of services running. And this is what drives the service discovery, enables you to always be able to route by service name to anything that's running in a cluster and nothing that isn't. So it's pretty cool. Okay. Well, I'm way ahead of time. I must have been talking quickly. And the other bonus that we get by using HA proxy and is zero downtime deployments, as I was saying earlier. HA proxy is able to, let's say you have 3 instances of your API containers running in your cluster, and you want to deploy a new version of it. Then with HA proxy, you can sort of deploy 3 more, and then remove the other 3 from the back end, and it will kind of allow those connections to finish, and then not create new connections with them, only create them with the new one, and then you can delete them. So that enables you to not lose any connections as you deploy new versions of the service, which is really cool. Okay, so that's all I really want to talk about with service discovery. I just want to talk a little bit about Docker multi-host networking. So often when you find yourself getting started with Docker and then you move to multi-host stuff, you find it quite difficult. And there's been a bit of discussion, I think, in the last year or so that maybe it's some criticism of Docker for this being difficult. In my opinion, this is quite unfair because there's nothing Docker are doing to make that difficult. It's just a difficult problem. If you have a bunch of services bound on different ports on the same host, and you want to wire them all up, like it's kind of messy, really, isn't it? It's nothing to do with Docker. And also, in trying to resolve this, building Swarm, which is really cool. It kind of takes all this away from you. Then it's like, oh, Docker are building this, themselves. We want to build this. Okay, fine. Well, you can't complain about both of them. I think that's also a bit unfair. I think that it's a symptom of when someone comes along in technology and makes something so much easier for us. Now we're able to do these reproducible stacks. We can move containers, the same ones from laptop into the production, and it's just awesome. And then we find that like some other things that were hard that we never really dealt with before because we didn't do this so much because it wasn't so easy. But now we're complaining about that. I think it's kind of funny. So I think difficult doesn't mean bad. Multi-host Linux container networking is complex, as I was saying before, and that's got nothing to do with Docker. But Docker, like before Swarm came along, or was coming along, then it's a fairly low-level building block for building a platform. It's a tool to make Linux containers easy, which is a particularly low-level problem. So these problems are bound to be difficult, is what I'm saying. Given my experience of building something like a platform as a service, where I found issues with Docker is not to do with multi-host networking at all, despite that being kind of complex. It's more that more with the Docker daemon, not qualitatively, but just the way that, as someone who's building a platform rather than just hosting a few things on some boxes, then I feel that I don't have full control over the processes and the containers that I'm starting and stopping, because in fact Docker is starting and stopping them. I'm just asking via the API, asking the Docker daemon to do it. And I feel that if you want to use, not everyone wants to use Docker like this, but if you want to use Docker as a building block for a platform, then you want more control than that. So that would be one issue I would have. And I think that feeds into the issue of composability. You will probably hear something about this in a talk about PowerStrip today. But with tools like Weave and Flocker, historically they've had to wrap the CLI in order to get some sort of, because you can't compose it with other things. And I think that that this, for me, is something I like a little more about the app container spec and Rocket, is that you can kind of just, you can run containers underneath, you have more control over the process hierarchy, let's say. It's not all within the Docker daemon. But yeah, I'm not trying to be controversial. That's just my experience as someone who's building something as a platform, using a Docker as a building block rather than just to sort of run services and things like that. Okay, so to summarize, a bit ahead of time. So a platform as a service that's designed for maybe like 12-factor apps needs to be really dynamic. You can't do static startup time service discovery. And I think if you stop anything short of something fully dynamic like what I've described, then it's just not really going to work. And yeah, so service discovery I think needs to be done either with something like Weave DNS or Flannel, or Console for that matter, or a dynamically configured load balancing proxy. Docker networking can be difficult. That's not a problem. Don't think it's a big deal. But also, I think Docker is awesome. All the things that it makes so much easier for us, like the fact that we're here, just means like so much has changed. So, great. That's all.
Thank you very much.